Welcome to the lesson 31 of industrial instrumentation. In this lesson and the subsequent lesson, that means lesson 31 and 32, we will discuss basically the dissolved oxygen sensors. Dissolved oxygen sensors was not that important, I mean sometime back, but due to the evolutions of the biotechnology in a very big way. So, this is to be considered very thoroughly, and also it has a tremendous application because the newer the bioreactors are coming up in the markets and lots of new product are coming, like I mean medicines, then antibody, which is basically the growth of cells. So, and in this particular situations, we must consider the dissolved oxygen sensor. That is one of the only sensors which can measure the dissolved oxygen concentration rather than the partial pressure of the oxygen in a liquid medium, and this will give you a lot of other informations which is not exactly measurable, which usually we have to estimate. So, that is the reason this is also this these dissolved oxygen sensors we brought under the industrial instrumentations, and it has also I should say that it is also used as a measurements of the dissolved oxygens in environments like the water treatment plants and the water discharged, where it is in the because there is some safety level of the water dissolved oxygen concentration, which is essential for the living animals like fish and others, algae and all those things, right. So, that is the reason we have taken this. Now, let us look at the contents of this lesson 31. Dissolved oxygen sensors. The contents are, in this particular lessons we will basically we will see this is a probe, actually the signal conditioning circuits, all those things will be discussed later on. So, basically like a pH probe, we will discuss here the dissolved oxygen probes. We have an anode and cathode, we will see all this in details. So, we will discuss the various construction, what is the theory behind this, what is the chemical equations inside this, all these things will be discussed. The typical constructions, dimensions, all those things will be discussed. Polarographic electrode. There are two types of electrode we will find. One is a polarographic electrodes and there is galvanic electrode. One need power supply and that don't need, right. So, we will consider the one which has usually do not does not need any power supply or a bias, that is called the galvanic electrode. Then basically we will consider theory of operation. The details constructions of these electrodes will be discussed in that subsequent lesson, that means in the lesson 32. At the end of the lesson, the viewer will know the working principles of the dissolved oxygen sensor, the electrodes of the dissolved oxygen probe, what are the different electrodes, one layer and three layer model. You will find that there are two types of model available. One is called one layer model of the dissolved oxygen sensor, as the three layer model of the dissolved oxygen sensors. Okay. Then we will discuss the reactions at the anode and at cathode of the electrode. So, there are chemical reactions which actually occurs in the both anode and cathode. This also will be discussed in details. Clear? Now, introductions. Let us see. The dissolved oxygen sensors or electrodes have been widely used both in research and industry. Okay. In the academics also we are using this probe to measure the dissolved oxygen concentration, and also industry is also where they are producing some biotechnical product, biotechnological product like medicines and all these things like the your antibody, then antibiotics, all those things you will need this type of sensors. Now, compared with the chemical analysis, now other way you can measure the dissolved oxygen concentrations or partial pressure is a chemical analysis. That means, you take out a sample and you make the chemical analysis. There is lot of limitations of that type of chemical analysis, because what will happen that you have to make offline, you won't, it is not very easy to get electrical output. So, if you want to control the dissolved oxygen concentrations inside the liquids, you cannot do it. Okay. So, in that case this the membrane based electrode, which is called the or membrane covered electrode, offers several advantages, right. That is the reason I am telling, compared with the chemical analysis, the measurement of dissolved oxygens in water by membrane covered electrode offers several advantages. They are as follows. What are those? Simplicity. Their design is very simple, Okay. Less interference by other solutes in the water. It does not matter whether, because if you have a chemical analysis, if you want to measure the partial pressure of oxygens or the diesel oxygen concentration, so the if you have some I mean other solutes, that will also react with your sample. So, that will create problem, you will not get the exact value of in situ measurement with lower time constant. You know, in situ measurements is basically new terms in the instrumentation, that is basically means the on the site measurements. In the bioreactors, you will find that there are various parameters which usually we measure, we cannot measure, but those also when you write the I mean state equations, you will find that those parameters are to be incorporated. One of those are like concentrations, I mean dissolved oxygen concentration is one, then we have a concentration of the product, concentration of the substrate. All those things will be unmeasurable. You cannot measure those quantity, only you can, online measurement is not possible. So, you have to take out, and there are few in situ sensors have been reported, but it is not much of use, right. So, only parameters which you can measure is the dissolved oxygen concentrations by the electrical output. So, it is in situ measurement, that means on the site you can immediately measure, you do not have to make a chemical analysis of your sample. Continuous measurement is possible whenever you can make the continuous, because it is electrical output. So, the continuous measurement also will be there also. Accordingly, if the continuous measurement you have, then obviously you can do the you can make the control also, okay, so that you can precisely control the dissolved oxygen in a particular medium or liquid. Real time control, that is I said the real time control of dissolved oxygen concentration in bioreactors or wastewater treatment plant. This I was talking about. You see the many places the water are discharged. Okay. Now, if you discharge those water as it is in a environment, that will create, because the plants and the animals, okay, marine animals, they need some sort of oxygen when they want to survive in a particular liquid. There is a particular concentration. That is the reason you will find that if that concentration goes down, the fish and other animals will die. Now, once you discharge those wastewater, so in an environment, that means in a swamp or something like that, so or pond, you must treat that, you must know that what is the dissolved oxygen concentrations or partial pressure of oxygens in that particular liquid. In that case also we need some in situ measurement, so that we can take care and make some artificial increase of dissolved oxygens in that particular liquids or the wastewater plant. And bioreactor, as I told you, it is a vital parameters which is only measurable parameter. Not only that, it is only measurable parameters in the bioreactors. Bioreactors actually I should define as it is basically a medium or reactors where the biological cells are grown. Okay, that is the reason we are calling, instead of calling simple reactors, you know, heard of chemical reactors, we are calling bioreactors because cells are grown. It does not matter whether it is an animal cell or a simple yeast, these are all bioreactors. Now, dissolved oxygen sensors have been developed for different areas to meet the requirement of the specific applications. Okay. There are various applications, and accordingly the people made different types of dissolved oxygen concentration measurement. Okay. The examples are the steam sterilizable DO2 probe suitable for bioreactors. Now, you know the bioreactors, if I take an example of the bioreactor, it looks like this. If I take a white page, it looks like this. I have a reactor here. This is a star tank reactors. Okay. I have a stirrer, right. It consists of blades, 3 or 4, 5 blades. See, it will rotate, it will look like this. There are several blades. Okay. Now, this is called impeller of the bioreactor, right, and this is the tank in which we have medium. So, tank will look like this one. So, tank is liquid is there and it is continuously rotating, okay, either in clockwise or anti-clockwise directions. If it is there, so what we will find that there will be some ADs will be formed which will look like this. Okay, like this one, some swirl will formed, this is eddies. This is tank and this is swell. Okay. So, it is continuously rotating, and if you increase the rotation, so what will happen, this is called the CSTR. Okay. CSTR is the continuous start tank reactor, right. This is called the continuous start tank reactors, we can see here. Okay. This is called the continuous start tank reactors are various type. You can have a bubble column reactors, you can have a CSTR, continuous start tank reactor. Now, the basic principle is nothing like if you increase the blade speed by, because this impeller is rotated by a motor. If you increase the motor speed, what will happen, that you see the oxygens is very difficult. One thing you must know, that it is very difficult to dissolve oxygens in a liquid, right. Now, only places where the oxygens will be dissolved is through this top surface. Okay, to the top surface, and top surface, whenever these oxygens are getting in contact, it is dissolves, and it is this top surface is getting saturated with oxygen. So, this top surface is to be refreshed, that means this lower surface of the water will go to the top like this one, so that it will get more and more oxygen. Now, if we increase the speed of this impeller, what will happen in this CSTR, continuous start tank reactor, there is a frequency of this water which is coming from the top from the bottom to above, okay, or the refreshing of this water top surface will be faster and faster. If it fast, then what will happen, that more and more oxygens will be dissolved. If you lower the speed, so the dissolved oxygen concentration also will decrease, right. This is the basic principles of the bioreactor, because the cell which will grow inside the reactor depends on the oxygen concentrations. It does not end here, because this dissolved oxygen concentration is a very vital parameters in any bioreactor, because that you know that the cell growth, by if I look at the cell growth, that whenever if I continuously measure these dissolved oxygen concentrations, you will find that initial stage, what will happen, that initial stage there will be a good consumptions of the dissolved oxygen. Okay. So, the cell concentration, that means the dissolved oxygen concentration will fall, right, slowly fall, because it is more and more cell is getting. Now, after some time you will find that the this concentrations is getting saturated. That means that during that time the cells are no more consuming any oxygen from the liquids. Okay. So, the health of the cell, that means the growth of the cell can be predicted also from the dissolved oxygen sensors output. It might be the current or voltage. Okay. Now, after some time we will find that the concentrations are getting increased. That means during that time the cell is totally saturated, there no more cell will be grown. That is the time we should take out the cell from these biological cells from the reactors. So, I can see that the dissolved oxygen plays a key role, not only to maintain the growth of the cell, but also to tell that whether the entire reaction has is complete, also the time when you should take out the cell from the reactor itself. Okay. So, this is very important, and this is only parameter, as I told you, in the bioreactor which is measurable. Now, this if you refresh these things continuously, what will happen, this it will be get newer and newer surface on. Also, you can do one thing, that means that if there is a if there is oscillations of these liquid columns, you will find that dissolved oxygen also will oscillations of the liquid column, you will find that means suppose if you have a liquid here in the two columns, you will find, and if you by forcibly if you can make the oscillations, so that the dissolved oxygen will be also getting, the oxygens will be dissolved in the liquid through the falling film through this one, right. This is another way. There are also bubble column reactor. In bubble column reactor, what will happen, if I take a new page, the oxygens are purged through a pipe, and it is going out, right, like this one, through in the liquid, right. So, here what will happen, again you will find that the oxygens are getting dissolved through this bubble column. There is a various various method of getting oxygen dissolved, but you have to measure that is either through to get a continuous measurement, either you have to make through a galvanic sensor or through a polarographic sensor. So, that is called now these reactors is you have to be basically to be sterilized. So, this DO2 probe, there are some DO2 probe which is suitable for making the sterilizable. That means, this probe is to be sterilized. How will you sterilize? You will, I mean, at the you have to be heat the entire reactor along with the probe, DO2 probe at 120 degree centigrade, which by superheated steam you have to do that. That means, from the boilers you have to pass that steam, so that the oxygen will be sterilized. Oxygen microelectrode for DO2 measurements in human tissues, right. Then the first responding sensor for respiratory gas analysis, because in many cases the patients need to feed the oxygen. So, that during that time, that means you must know that because pure oxygen is very difficult, there is some from impurity is always there. So, how much is impurity also you can know from the dissolved oxygen. Measurement of trace of oxygen in boiler feed water, because boiler feed water is also necessary in a thermal power plant, that the feed water is how much oxygen is there. So, that also can be online measurement is possible through this DO2 probe. Three broad areas I should say where the measurement of DO2 concentration is essentials are biochemical engineering, then microbiology. Biochemical engineering obviously includes the bioreactor, microbiology, and environmental engineering, that means wastewater treatment plant and all these things. Okay. So, there also we need to measure the dissolved oxygen concentration. So, the partial pressure of the oxygen in the wastewater, which is getting discharged to the environment. Now, principal operation. There we have polarographic electrode, as I told you. First we will discuss the polarographic electrode, then we will discuss the galvanic electrodes. Principle is basically same, one in bias, other do not need. When an electrode of noble metal such as platinum or gold is made 0.6 to 0.8 volt negative with respect to the reference electrode made of calomel or silver chloride in a neutral potassium chloride solution, the dissolved oxygen is reduced at the surface of the cathode. This is the basic principles of the dissolved oxygen sensor. It does not matter, I mean whether it is polarographic or galvanic. This phenomena can be observed from a current voltage diagram called a polarogram of the electrode. Okay. This is called the polarogram. We will see the polarogram very soon. As shown in figure 1a, the current increases initially with an increase in negative bias. Okay. Then it reaches a region where the current becomes essentially constant. It will be very clear from the next slide. In this saturation region or the plateau region of the polarogram, the reaction of the oxygen at the cathode is so fast that the rate of reaction is limited by the diffusion of the oxygen to the cathode surface. Okay, this is our polarographic electrode. You see, this is a polarogram. You see here. Okay, this is this is the negative bias we are giving. As you increase the negative bias, you will find that the output, relative current output will increase. So, at that some position you will find there is a saturation, and after that is a certain increase, that is different thing. You will find there is a saturation or a plateau region. Okay. So, this is a percentage of oxygen, so the partial pressure of oxygen, it is increased as you can see. So, it is 1.5, as you increase the bias you are getting the saturation, then it is increases. It is with the concentrations of the oxygen is 7%, and if you increase the bias, initially it will make linear, then it will get saturated like this one. Now, in the subsequent you see this is a calibration curve. So, I have plotted here the bias voltage. Okay. Here bias voltage is 0.7 volt. I have plotted the percentage oxygens on the x axis, okay, and I am getting the relative current. So, it is almost linear curve as you can see, right. This is called the calibration curve. Clear? When the negative bias voltage is further increased, that the current output of the electrode increases rapidly due to the other reactions. Let us go back. You see, as shown in figure, the current increases initially with an increase in the negative bias, is not it? As you increase the negative bias, current increases, then it reaches a region where the current becomes essentially constant. In the saturation region, plateau region of the polarigram, the reaction of oxygen at the cathode is so fast that the rate of reaction is limited by the diffusion of oxygen to the cathode surface. That is the reason I am getting a plateau region, okay, or a saturation region. This you see, as you increase and the bias, it is slowly increases, then it is so fast that I am getting a saturation region here. Same, as you increase the bias for a particular concentration, negative bias, so it is increases, then it is getting plateau region. After that is a slide, there is a drastic increase of the current. When the negative bias voltage is further increased, the current output of the electrode increases rapidly due to other reactions, mainly the reduction of water to the hydrogen, right. So, that is a different thing, we are not concerned with that region, clear. Now, if a fixed voltage in the saturation region of the polarigram is applied to the cathode, if a fixed voltage in the saturation region of the polarigram is applied to the cathode, then the current output of the electrode can be plotted for different dissolved oxygen concentration, that is figure 1 shows such a calibration curve. Okay. What he is saying that the fixed voltage in the saturation region of the polarigram is applied to the cathode, fixed voltage I have given in the previous curve, you see we have given a fixed voltage of 0.7 volt, right, cathode. Then the current output of the electrode can be plotted for the current dissolved for the different dissolved oxygen concentration. Okay. Current outputs are plotted on the x axis dissolved oxygen or percentage partial pressure of the oxygen, and the figure B shows, and which is called the calibration curve of a polarographic electrode for dissolved oxygen measurement, clear. It has to be noted that the current is proportional not to the actual concentration, but the partial pressure. It does not matter. So, if the partial pressure is high, the concentration also will be high, but due to the activity of the equivalent partial pressure of the dissolved oxygen, which is often referred to the oxygen tension, right. A fixed voltage between 0.6 to 8 volt is usually applied as the bias voltage or polarization voltage when using silver chloride as a reference electrode, right. When the cathode, anode and the electrolytes are separated from the measuring medium with a plastic membrane which is permeable to gas, but not to the most of the ions, and when most of the mass transfer resistance is confined in the membrane, the electrode system can measure the oxygen tensions in the various liquids. Okay. So, what is the key? A plastic membrane which is permeable to gas, but not to the most of the ions. So, the gas will permeable through this medium and through this membrane, and when most of the mass transfer resistance is confined in the membrane, the electrode system can measure oxygen tensions in various liquids. This is the basic operating principle of the membrane covered polarographic DO2 sensor. This is the basic requirement or basic operating principles of the membrane covered polarographic DO2. In both the cases, we will find we may use the membrane, it will be clear after some time, right. A polarographic electrode is shown in figure 2. For polarographic electrode, the reactions are as follows. Okay. I will show the figure 2 after some time. Reaction at cathode, O2 plus 2H2O, 2 electron gun plus 2 electron is equal to hydrogen peroxide plus hydroxide H2O2 plus 2 electrons, it is 2 hydroxide. Now, reaction at anode AgCl, it will be AgCl plus C, 1 Cl is negatively charged. So, it will release 1 Cl and we will get AgCl with 1 electron. Overall reaction 4 Ag plus O2 plus 2 H2O, 4 chlorine plus equal to 4 AgCl plus 4 hydroxyl ion, right. The reaction produces alkalinity in the medium, quite obviously you can see 4OH. So, it will make it alkaline, and a small amount of hydrogen peroxide is also produced, right, that we have seen in previous. Now, this is our polarographic electrode, you can see this electrode. Okay. It is basically a cylindrical in nature. You see I have an ammeter which is basically a microammeters. Okay. We have a polarograph, we have a cathode, there is a membrane, this is the membrane you can see. Okay. This is our membrane, you can see here, this is the membrane, permeable membrane. The gas can permeable, most of the ions will be blocked here, because this entire thing, please note, will be dipped in the reactor itself or in the wastewater. Okay. This is the tank or the reactor tank, or in the wastewater, this entire thing is to be dipped. clear, entire assembly. So, this whole assembly, this is our probe, this is our total probe, right. You see electrolyte is here, we have put a anode here, insulation is here, there is a membrane and there is a cathode, clear. This is the diagram and we have given a bias. We have seen that if we increase bias, obviously the output will increase with the concentration, right. Now, for a fixed bias, what will happen if I obviously I will for different increased concentrations I will get the higher relative current outputs, which will be utilized for the measurements or for the control of the dissolved oxygen partial pressures in the liquid, clear. Now, if I draw the actual diagram, it will looks like, because you see this electrode, as I told you, it should be come in the tank, and this entire electrode actually will find that it will be in the form of it will be in the form of, it's a very handy things, and it will be basically cylindrical in shape. Let us look at that diagram. Let me take a white page. Okay, it will look like this. Type this one. So, it will look like this. You see that it is cylindrical in shape, it is the entire thing. Okay. So, it will come down here, sorry, it will, I am going to take a new page, it is a, it will come down here and we have a probe here. Okay. We will go down, there is an anode, cathode, this is cathode, right. So, entire thing like this one. So, there is another one, okay, it looks like this one. Okay, the membrane is here, right. We need later support and all this thing, that is I am not discussing, because it cannot hang in a yard, as you know, we need a support. Okay, and this will work as a your anode, and this will work as a cathode of your systems, right. And we have a glass cylinder, so entire thing we put on a glass cylinder, which looks like this, it's coming like this. On a glass cylinder like this one, okay. It will looks like this. There are various dimensions, I mean typically in IIT Kharagpur we made it like this one, and we put a Teflon here. Okay, nowadays Teflons are very extensively used, which is 100 micron thickness. Okay, this is this diameter is 2 centimeter. Okay, sorry, this diameter is 2 centimeter, and this diameter is 1.4 centimeter, 4 centimeter like this one, clear. And this is quite small, this diameter is 0.75 centimeter, clear. This is all the dimensions. It will go to anode, and this will also will get a signal here. I am not showing the bias, because the galvanic also has the same type of forms, and this can be made of anode, can be made of lead, this lead, and cathode can be made of silver. Right. Okay, these are polarographic electrodes, insulations. We have membrane here, we can use a Teflon here. This is a galvanic electrode. Okay. So, this is we have shown that this is an ammeter, there is no bias, electrolyte is here, anode, insulation, membrane and cathode. Galvanic electrode, the galvanic electrode is shown in figure 3, okay. Figure 3. The galvanic electrode is different from the polarographic type in that it does not require external voltage source for the reduction of oxygen at the cathode, that is the basic difference. When a basic metal or base metal such as zinc, lead or cadmium is used as the anode and noble metals such as silver and gold is used and the cathode, the voltage generated by the electrode pair is sufficient for spontaneous reductions of oxygen at the cathode surface. In IIT Kharagpur, actually in our bioprocess instrumentation laboratory, we have developed a DO2 sensors which is giving quite good response, where we are using lead as a anode and silver as a cathode. The electrode reactions of the silver lead galvanic probe is as follows. Reaction at cathode AO2 plus 2H2O plus 4E, 4 electron equal to 4 hydroxyl ion. Reaction at anode Pb to its I mean positively charged, then and 2 electron, right. So, looks like this. Overall reactions will be O2 plus 2 Pb plus 2 H2 equal to 2 Pb OH2. As shown above, the oxygen is reduced via 4 electron reaction. This reaction is called the 4 electron reaction, and unlike the polarographic probe, the electrolyte does not participate in reaction, but the anode is gradually oxidized. Okay, that is one problem with this. Unlike the polarographic probe, the electrolyte does not participate in the reaction, but the anode is gradually oxidized. Therefore, the life of the probe depends on the exposed surface area of the anode. Whether the polarization voltage is applied internally in the case of galvanic or externally, which is applied in the polarographic, the operating principles of the electrode remains same. Okay. Operating principle same, whether you are applying a galvanic, I mean polarographic, in the case we are giving it externally, in the case of galvanic it is generated internally. There are some gases which reduce in the presence of 0.6 to 1 volt in the test medium. Examples are halogens, which is chlorine, bromine and iodine, and oxides of the nitrogen. It will lead to erroneous output in the measurement systems. Okay. So, you have to be very careful if you have the presence of this type of gas in the liquid where we are interested to measure the dissolved oxygen. Theory of operation. The basic principles of measurement for the membrane covered DO2 probes can be summarized as follows. If the oxygen diffusion is controlled by the membrane covering the cathode, the current output of the probe is proportional to the oxygen activity or the partial pressure in the liquid medium. Okay. Basic principle is same. The following assumptions enable the mathematical analysis of the pressure profile of oxygen in the liquid and the current output of the dissolved oxygen sensor. What are those assumptions? Let us look at. The cathode is well polished and the membrane is tightly fit over the cathode surface, so that the thickness of the electrolyte layer between the membrane and the cathode is negligible. So, we are assuming there is absolutely no layer of the electrolyte in between the cathode and the membrane, usually which is a Teflon membrane. The liquid around the probe is well starred. Okay. So, it is mostly in the case of wherever you are measuring, it is a well starred liquid. So, whether you are using in the bioreactors or the wastewater, it is well starred. Well starred and agitated, so that the partial pressure of oxygen on the membrane surface is same as that of the bulk liquid, because we will need these assumptions, otherwise very difficult to calculate establish the current equations. Okay. So, the oxygen at the membrane surface is the same as that of the bulk liquid. At present, we consider the oxygen diffusions occur only in one direction, that is perpendicular to the cathode surface. Okay. We are assuming in the one directions only, that is perpendicular to the cathode surface. It is so called one layer model, but it can be modified to include the effects of the other layers, as will be discussed later. Now, suppose the electrode is immersed in a well agitated liquid and at time 0, the oxygen partial pressures in the liquid is changed from the 0 to PO. According to Fick's second law, the unsteady state diffusion in the membrane is described as delta P, okay, del P by del T, that means partial derivative of P with respect to T equal to dm d subscript m del square p by del x square, double derivative of partial derivative of p with respect to x is equation number 1, where dm is the oxygen diffusivity in the membrane, okay, in the Teflon membrane, x is the distance from the cathode surface. It will be clear from the figure 4 what is actually 4. The initial and the boundary conditions are P equal to 0 at T equal to 0, initially there is no partial pressure, P equal to 0 at x equal to 0, okay, at the cathode surface there is no, and P equal to P naught at x equal to Tm. T is the thickness of the membrane, please note T is the thickness of the. So, we start at the 0 and we ends at T equal to Tm, x equal to Tm. So, this is the one layer model. So, we have as we shown that is we are considering the perpendicular the cathode surface, this is our cathode surface. Okay. So, we are considering at x equal to Tm. Please note this is the thickness of the membrane, because you remember that the reactors are looks like this, I mean sorry, the membrane, they have a membrane here, is not it. So, we have a cathode here, clear. So, perpendicular to cathode surface. So, as we are going like this one, these directions, clear. That is where this is x equal to 0 and this x equal to this x equal to 0 and this x equal to Tm, that means thickness of the membrane. So, we are considering that this will to be insert in a tank or liquid medium, right, x equal to Tm. So, x we are from the cathode surface we are getting, this is our thickness of the our membrane. This is again we are coming to the liquid, this is the one layer model of the electrode, right. So, we have 2 layer model or 3 layer models also, we have a electrolyte. So, we are assuming there is absolutely almost there is no electrolytes in between this cathode and the membrane surface, right, that is actually we are making the assumptions, where Tm is the membrane thickness and the first boundary conditions, which is equation 3, assumes very fast reaction at the cathode surface, and the solution of the equation 1 with boundary conditions will be given by P by P naught x by Tm summation n equal to 1 to infinite 2 by n pi into multiplied by 1, I mean 1 to the minus n sine of n pi x by Tm exponential minus n of x n square pi square dmt by Tm square. The current output of the electrode is proportional to the oxygen flux at the cathode surface. Now, NFA Pm will be equal to multiplied by partial derivative of P with respect to x at x equal to 0, that means at the cathode surface, where NFA and Pm are the number of electrons per mole of the oxygen reduced, and Faraday's constant, which is F is the Faraday's constant, A is the surface area of the cathode, which is very easy to calculate because it is a pi r square or pi d square by 4, and the oxygen permeability Pm is the oxygen permeability of the membrane respectively, right. Okay. A is the number of electrons per mole of oxygen reduced, A is the Faraday's constant, A is the surface area of the electrode cathode, and Pm is the oxygen permeability of the membrane respectively. The permeability Pm is related to the diffusivity of the oxygen by the following expression. What is that expression? Pm equal to dm into Sm. What is Sm? Let us look at, where Sm is the oxygen solubility of the membrane, and from equation 5 and 6 the current output IT, current output, because actually that is the only measurement, that is the reason we are going for the membrane based electrode, membrane covered electrode, otherwise we can make the chemical analysis. We need this current output for continuous measurements or continuous control of the partial pressure of oxygen or dissolved oxygen concentration either in the bioreactors or in the wastewater treatment plant. As function of time will be expressed as follows. This is equal to, you see, the current output IT equal to N F A P M by T M multiplied by P O 1 plus 2 summation n equal to 1 to infinity minus 1 to the power n exponential minus n square pi square d m t upon T m square. This is equation number 8. The pressure profile and the current under steady state condition can be obtained, nothing but what will happen in the steady state condition, this term will go, this term will be 0 because steady state condition, because it is a negative exponential power, then what will happen if there as the time grows. So, this will be larger and larger because it is 1 upon this. So, this will become this converging. So, it will be 0, right, as the time grows. So, only these portions will remain, that is the steady state current output, clear. And the pressure profile and the current under steady state condition can be obtained from the equation 5 and 8. Let us look at what is 8. and 5. So, we are combining 5 and 8. So, we are getting that P by P naught equal to x by T m, right. And I s steady state current, you see that I t is a total current or transient current, I should say, not total current, transient current, equal to N F A P m by T m into P naught, equation number 10. At steady state, the pressure profile in the membrane is linear and the electrode current is proportional to the oxygen partial pressure of the bulk liquid, right. So, equation 10 forms the basis for DO2 probe measurements. Okay. What is the equation 10? This is equation 10. Okay. So, this is our basis for all, okay, DO2 measurements or DO2 probe. Another important considerations in the time response or the time constants of the probe. How we can make the time constant lower and lower, because you see if the time constant is large, though the bioprocess usually, I mean, we do not need very fast measurements. Typically, we can make 5 to 6 minutes, most of the reactions are like, because you see the reactions in the bioprocess usually it is quite long, I mean it sometimes it 30 hours, I mean 40 hours. So, you do not need like a, I mean very fast sampling, I mean you do not have to make the measurement very fast, you can measure every 6 minutes, 10 minutes, but still that, I mean you must consider the time constant or the response time of your DO2 probe, right. These are important issues or important parameters of a probe. According to equation 8, the probe response depends on the probe constant k, defined as follows, that k equal to pi square into dm by Tm square, okay, equation number 11. A large k, which means a thin membrane, okay, and or a high dm, okay, diffusibility large, results in a low value of time constant, quite obviously, right. A large k, which means the thin membrane is thin and diffusivity is high, for the membrane is high, results in a low value of the time constant. So, this will make the time constant low and the consequence, the probe response will be very fast. However, the assumptions of the membrane controlled diffusions will be no more valid in these conditions. It is very contradictory. So, one way we are reducing the time constant also always should be lower for any instrumentation system, for any sensors, okay, lower is better. Thus, a compromise has to be made for an optimum performance of the DO2 probe. Thus, a compromise has to be made for an optimal performance of the DO2 probe. Limitations of single layer electrode model. In reality, the assumptions 1 and 2 made earlier are not entirely satisfactory. Okay. So, we have made some assumptions at the very beginning to establish or to build the theory are not entirely satisfactory. Often there exists a finite thickness of electrolyte layer between the cathode. Okay. We have assumed that there is no electrolyte layer in between cathode and the membrane, but there is a finite layer of electrolyte in between cathode and membrane. Okay. And the membrane, because of the roughness of the cathode surface, though we claim that the if the cathode surface and membrane is absolutely plain, okay, so there is no chance of any, I mean electrolyte coming in between, but if there is a slight roughness, so a layer of liquid or layer of electrolyte will come in between the membrane and the cathode. Okay. So, that is to be taken care. In the single layer model, we have not taken care, we have assumed that that is 0, thickness of the electrolyte is 0 in that region. Also, a stagnant liquid film always exists outside the membrane, even at very high liquid velocity, even though we have a very good start, I mean because starting you are doing, you see in the reactors. Okay. Now, usually there will be liquid, I mean because it is inside, okay, the liquids it will be to inserted, I mean. So, always there is a stagnant liquid, okay, liquid film always exists outside the membrane even at very high liquid velocity, clear. That means, the liquid which is in contact with the membrane, we are assuming that is a liquid film is existing, okay, which is stagnant. What is that? Look at very carefully, it will look like this one. Okay. So, we have you see the probe is like this one, we have a probe here, membrane. Okay. So, we have a cathode here and this we are inserting inside a liquid, is not it. This is our membrane This is our cathode, this is connected like this one. First of all, we are assuming that this cathode there is a layer that which we have assumed that the layer of thin liquid is, I mean, as electrolyte does not present in the case of one layer model. That is not true. If it is, there is a slight roughness, electrolyte will come in between. Secondly, the film, even though it is rotating, I mean this we have agitators either in the continuous CST, that means continuous start time bioreactors, or your other type of reactors. What will happen, that there is a continuous I mean movement or agitations of the liquid, even though we will have a thin layer in contact with this one will be stationary or stagnant, thin layer of liquid, right, in contact with the membrane. Clear? A more realistic model of the electrode is shown in figure 5, which is called basically 3 layer model. Okay, all the 3 layers, namely the electrolyte, the membrane and the liquid film have been considered. Okay, all the 3 layers have been considered. You see there we have considered, this is our electrolyte, in between this is our cathode. Okay, this is our cathode. I can take this one. This is our cathode. We have a membrane. After that, we have a definite thickness of the electrolyte. Then we have, this is a membrane thickness, Tm is a membrane thickness, and this is our liquid film thickness. Okay, you see it is slowly increasing. So, like this one, it is increasing. Okay, you see here after that we are getting the main liquid, bulk liquid, but here this is a film thickness which is in stagnant, okay, with the membrane itself. So, we have enlarged, though this is very small in the order of excuse me, in the order of micrometers, but just to explain to the students we have I mean elaborated it like this one. The effect of different layers on the electrode behavior can be estimated by using the one layer model. At steady state, the oxygen flux J through the each layer, what figure 5 becomes identical. Okay, but J equal to K naught into P naught, KLM P naught minus PM, Km multiplied by PM minus PE, which is we can write Ke into Pe, which is equation number 12, where K0 is the overall mass transfer coefficient and small k's represent individual mass transfer coefficient corresponding to the liquid film KLM, the membrane Km and the electrolyte Ke respectively. The overall mass transfer resistance 1 by K0 is then expressed as the sum of the individual resistance, which can be given like this one, 1 by K0, 1 by KLM is the liquid film mass transfer coefficient, 1 by Km membrane mass transfer coefficients, and 1 by Ke electrolyte, right. Equation 13 can be rewritten by using the oxygen permeability and the thickness of each layer as follows. Okay, we convert in layers, 1 by K0 equal to TL, okay, by PL, Tm by PM, Te by Pe, where TL, T, PL, Tm already we have defined, it is the thickness of the membrane, TL, T, PL and Pe are the liquid film thickness. This is the liquid film thickness, okay, this is the liquid film thickness, this is the electrolyte thickness, okay, the oxygen permeability of the liquid film, okay, liquid film only, and that of the layer itself, this is of the electrolyte itself, this is Pe. Clear? A completely stagnant liquid film was assumed here, although it is more accurate to use the convective mass transfer coefficient, it is becoming more complicated rather. Convective mass transfer coefficient, and the condition for membrane control diffusion becomes that Tm by Pm will much greater than TL by PL plus Te by P, equation number 15. This means that the relatively thick membrane, okay, with low oxygen permeability is required, which contradicts the requirement for lower time constants of the probe. That justify, I mean you can be, this can be justified because in the most of the these dissolved oxygen measurements, we do not need very fast response. For even controls, I mean if you can measure only 6 minutes or every 10 minutes, that will suffice. Same thing with the wastewater plant, treatment plants also, we do not need that fast. Even if we measure, if you have a sensor which can measure the dissolved oxygen, partial pressure of the dissolved oxygen or dissolved oxygen concentrations very frequently every second, that does not make any sense. because you need to control, if you want to control, that means increase the dissolved oxygen concentrations in the particular liquid. The mechanisms which you have to follow, that means increasing the stirrer speed or any other oscillations or anything, it will take a large time constant. So, there is no use of measurements of very fast, so that is a little larger time constant will be justified if you have a proper model in that sense. Okay. So, that is most important. This means that relatively a thick membrane with low oxygen permeability is required, which contradicts the requirement, because if you make the thick membrane low oxygen permeability, obviously what will happen, that the time constants of the system will increase. For a given cathode geometry, the resistance of the electrolyte is almost fixed. Okay. For the resistance of the electrolyte is fixed, that is not very problem, right, for a particular geometry of the cathode. Also, since the electrolyte is contained inside the membrane, it does not affect the measurement. Therefore, the condition for accurate measurements of dissolved oxygen becomes that T m by P m plus T e by P e much greater than T L by P L, which is equation number 16. When the individual resistances are taken into account, the steady state current output can be written as, when the individual resistance are taken into account, the steady state current output can be written as I s steady state current N F A P m by T bar into P naught. Okay. These equations already we have written, so we have just modified according to these expressions, right. Where T bar is defined as that T bar equal to T m plus P m by P L into T L plus P m by P into T. Okay. That is equation number 18. In this case, the probe constant K is modified as follows. We write K equal to pi square into dm diffusivity of the membrane upon T subscript small t dash square, with this equation number 19. What is the T T T? That will be clear from the next expression, where T subscript small t bar is equal to T m plus under the square root d m multiplied by T L over d L plus under the square root d m upon d E multiplied by T E, equation number 20. Equation 17 and 19 show that the steady state current decreases, okay, and the probe response time increases when there is a significant mass transfer resistance in the liquid film around the membrane, which is quite obvious, right. Normally, probes are operated such that the effect of liquid film resistance is negligible. It is achieved by using a membrane of low oxygen permeability and by the well agitation of the liquid around the probe. Okay. So, there is all this compromise we have to make. In fact, actually we in the IIT Kharagpur we have developed a DO2 sense. Now, DO2 sensing, if you look at, so actually it looks like this. If you look at the complete instrumentation diagram, so it will look like this. I have a DO2 probe, sorry. Okay, I have a DO2 probe. I am getting a current, okay, current output I s steady state current. This current is converted to the current to voltage converter, current to voltage converter. Then you have a voltage amplifier, okay. Now, it is easier to make, then we can convert to the typical current, because these amplifications will make us to the proper voltage, because most of the converters. So, we have a V to I converter here, because once it is current to voltage, this can be typically I will get the voltage. Usually typically current voltage is 0 to all the converter available for 0 to 5 volt, which will give you 4 to 20 milliampere. Okay. So, this can be done here itself, that means 0 to 5 volts, this will give you. Now, I am getting a current output which is 4 to 20 milliampere, okay, which is used for the measurements. As you know, industry that 4 to 20 milliampere is a standard. So, we will get like this one. Moreover, you see that we have used a a plot. What we found that we basically made we made in these measurements we made in a bioreactors, okay, in IIT Kharagpur in the bioprocess instrumentation lab, and we found that we got a consistently good results, though the result inconsistent obviously, but when we measure with the other sensors, so there is a slight offset that which is quite obvious. So, this galvanic electrode actually it worked very nice in our laboratory, right. So, with this I come to the end of lesson 31 of industrial instrumentations. Basically, we have considered the dissolved oxygen sensing here, and basic more details of the sensor, 4 different more details of the sensing will come in the lesson number 32. Welcome to the lesson 32 of industrial instrumentation. This is a continuation of lesson 31. Actually, we will consider here the dissolved oxygen sensor. We discussed basic principle of the dissolved oxygen sensors in details in the lesson 31. This particular lesson will consider the different types of electrodes, its calibration, type of membrane. These are the very important things for designing any DO2 probe, and type of type of materials which is used for making the electrode, especially the electrolytes, and what should be the suitable nature of the membrane also. That is also very important, because in some cases you have to sterilize the dissolved oxygen sensors when it is used in the bioreactor, or you will put in the autoclave. So, the temperature, minimum temperature there will be 120 degree centigrade. So, in that type of situations we will discuss, we need some sort of autoclaving and with a or some sort of sterilizations, and these particular lessons we will discuss all those in details. As I told you earlier, that it is a continuation of the lesson 31. Let us look at the contents of this lesson. Lesson 32, dissolved oxygen sensor 2. Contents: construction of electrodes, how the electrodes, what is there, what is anode, what is cathode, what type of material is used for making anode and cathode, what type of electrolytes we are using, where the membrane lies. So, all these things we will discuss.